We are athletes in sports engineering, and our product is the ReBal. My name is Olivia Gwynn, and I'm on the Duke track and field and cross country teams.
My name is Mackenzie Wilborn, and I'm on the Duke swimming and diving team.
My name is Clark Bullitt, and I'm on the football team. Our client, Zach Christofferson, is the head physical therapist for the Duke football team. He currently helps athletes returning from lower extremity injuries by taking them through exercises such as squats, deadlifts, and cleans. While doing these exercises, he needs to make sure that these athletes are properly distributing their weight so that they are gaining strength on their injured leg and do not have strength imbalances when they return to play later on. In order to make sure of this, Zach currently uses visual cues such as hip tilt or foot position to make sure that they are equally distributing their weight. However, he came to us to desire something that would be quantifiable in real time that could allow him to adjust athletes while they are doing these exercises to make sure that they have the best possible outcomes when returning to their sport.
To meet our client's need, we started to build our first prototype. Our first prototype was 24 by 24, so it was a little too big. It was also made of plywood, which had too much flex for our accuracy standards. We then moved on to our second prototype, which you can see here below. Our second prototype was made of 2 acrylic boards, each 12 by 12. Each also contained 4 load cells, 1 in each corner. We took the signals from the load cells into an Arduino Uno. We sampled the Arduino at 100 Hertz and took the signal into our computer using a direct connection. We displayed the signals on the screen, which you can see here to our left, using a serial plotter. You can see 3 signals, 1 for the right leg, 1 for the left leg, and finally a total resultant signal. We gave this prototype to our client, Zach, to use on 5 different athletes over the span of a month. He gave us a lot of good feedback, some of which was very crucial to our final design.
Here's our final prototype. Based on feedback given by our client, Zach, we have modified the design of our platforms. One of the specific changes is the size of the board. The platforms are each now a 12 by 18-inch surface area. This surface area accommodates a size 22 foot to easily fit onto the boards and perform various athletic activities. In addition to that, we have changed the feet of the boards. The feet are now built into each of the platforms, enabling easy calibration on uneven surfaces and improving the stability of both the boards. Finally, we also changed the microcontroller within the boards. We started with an Arduino Uno, and we have now changed the particle photon. The photon consists of a Wi-Fi module, enabling us to transmit data wirelessly from the boards to our personalized web application.
Now we are going to go through some more specific features of the device. The board you see on the left hosts most of the electronics, including the particle photon and the battery. The right device only hosts the 4 load cells as well as the amplifier for those cells. The 2 devices are connected via a micro USB cable. We chose this cable because it is very easily replaceable, and we did not have a good way to protect it from damage. Going more specifically to the device on the left, when you turn on the switch, it's indicated by a green light, and the particle photon will immediately begin connecting to the Wi-Fi in the area. We also included a battery in this device, and the battery is 3.7 volts, and you can easily charge it off the wall power because it has a protection circuit. So you can simply plug in the device here and charge it whenever it gets low. It has a battery life of about 12 hours that we've calculated, and it seems to work perfectly. This is the bottom of our board. As you can see, we encased all of the wires and electronics in either acrylic or 3D printed covers. We also housed all of the load cells, which are inside these inserts here, up inside the board itself. The feet here are aluminum, and they press up on the load cells to actually get the force. And we also added handles, which are very sturdy and provide a good grip to allow them to be transported easily and safely from place to place. Let's go.
Here we have our final prototype, along with our personalized web application as requested by our client, Zach. When Mackenzie steps on the board, the data can be transmitted wirelessly and in real time to our application. To access this data, the user just has to click on our button saying Get Data, and it streams it through as such. The data on the left is shown by the blue line and the blue bar graph, while the data on the right is shown by the red line and the red graph. The green line on the bottom also shows the total force distributed between the 2 plates. Our client requested that we have both a bar and a line graph, the line graph to show more sudden movements and the change in pattern of activities throughout the 5-second period. The bar graph is also shown for when more stable activity is taken place, and you can see a more accurate reading of the force distributed.
these force plates have had a relatively big impact on what we have done with our athletes post injury. So one of the challenges that we face is when you have an athlete, let's say with a lower extremity injury, and you're going through various stages of rehab, they can develop compensation patterns without even being aware of it. And in rehab, what we try to do is find ways to help them either avoid having those compensations develop, or give them tools to use in order to overcome those compensations. So what we've found with the force plates as we've been using them is it's a great way to accomplish both of those things. One, it provides a visual cueing so that they can overcome that compensation pattern and progress towards appropriate movement. And two, it's another way outside of some of the other components that we use to help retrain their movement patterns.
In conclusion, we were able to build a device that Zach could use in his athletic training room. He used the device to help some of his athletes get back on the field, which was the goal of our project. We improved upon that device to meet all of his customer needs, and we did it all within under $240. We're very proud of what our final device has accomplished, and we have so many people to thank. We would like to thank our professor, Kevin Caves, and our client, Zach Christofferson, for working very closely with us this semester and for helping us complete our project.
Thank you also to Dr. Eric Richardson, Dr. Mark Palmieri, and Matt Brown for helping us identify the needs of our problem last semester and helping us with all technical difficulties this semester.
Also, thank you to Greg and Steve in the machine shop. We had never machined anything before, and they really walked us through the entire process very well.